The last few lessons have been dealing with losses in pipes. Those have been assume the pipe is straight, laminar, turbulent, find the loss coefficient, find the head loss. But a lot of pipe systems aren't just straight sections of pipe. You need bends, you need curves, you need tees, you need other things going on. And there's also going to be losses through those components. And so those are called minor losses or component losses when you get losses through those. And that will be the subject of today's lesson. So the major losses were characterized by the friction factor F. Minor losses are characterized by something called a minor loss coefficient, capital K. These are generally determined experimentally, so what you do is you measure either the head loss through that component, and then you can experimentally determine the value of K, or measure the pressure loss. Either way, that's going to give you a value of K. And now that they've determined these things experimentally, you can find the results in a bunch of tables, graphs, figures for various components and systems. So we'll see those next.
So for entrance flow, if you have a pipe in a tank, so the water is just coming from the tank into the pipe, there's a loss associated with that. And it really depends on the shape of the entrance. So there's a few different varieties of that shown in this figure 12.4 in the textbook, and different loss coefficients associated with that. So for entrant flow, K is 0.8, sharp edge, K is 0.5. Then if you round it, you get a little less loss, so 0.2 for slightly rounded, 0.04 for well rounded. This also gives an indication of the exit flow. So if you go out of a pipe into a tank, basically the arrows going in the opposite direction, you'll also get a loss. Doesn't really matter on the shape in the exit case, always K value is 0.1. The next figure, 12.5, gives minor loss coefficients for contractions or expansions of pipes. So going from one diameter pipe to another, you get some loss associated with that. So contractions on the top, expansions on the bottom, is a function of area, so how big of a contraction or expansion you go through. And be careful with this figure because there's two different velocities, one on the left side, one on the right side, and the one to use is very important for these graphs. The next figure, figure 12.6, deals with smooth bends in the pipe. So this depends on the diameter of the pipe and the radius of curvature of that smooth bend. So you have a ratio of R over D. Various values give you different values for the loss coefficient K, as indicated in the table. And last but not least, table 12.2 gives K values for various components, elbows, bends, tees, valves, etc.
So what do we do with these values of K once we found them? Well, we can rearrange one of the formulas we saw before for K to get the head loss out of it. So head loss, minor losses are my minor loss coefficients K times V squared over 2G. Then to find the head loss through any single component, that gives me that. If I want to find the head loss through all of my components, because generally I'm going to have a lot more than one, I just take all these for each individual component and add them all together, and that's my total minor loss. If you want the total head loss, that's the sum of the major loss and the minor losses. So we take all the major losses, all the sections of straight pipe, where we have F, L over D, V squared over 2G, found like we did in the previous two lessons, and then add on to that all the minor losses, so all the sum of K's over times V squared over 2G's, and that's the total head loss for the system. One last thing to mention is that we're dealing so far with just circular pipes. Sometimes you have pipes that are not circular, usually things like AC systems, you have rectangular ducts. In that case, what we can do is define something called a hydraulic diameter. So DH is 4 times cross-section divided by the wetted perimeter. Wetted perimeter basically means where the fluid is flowing, where the wet sides of the fluid is touching, essentially. So again, for air conditioning, rectangular duct, have some length, some width, rectangular duct. Plugging that in here, my cross-section is L times W, perimeter all the way around, 2 W's, 2 L's, cancel 1 and 2's, so my hydraulic diameter in that case 2LW over L plus W, and basically can use that as a diameter in all the previous equations we had. Sometimes there's also a hydraulic radius that's important for some questions. Hydraulic radius is defined to be the cross-section divided by the wetted perimeter, so no 4 there, which means that my hydraulic radius is actually my hydraulic diameter divided by 4, not divided by 2, and that's just based on this definition, so be careful with that. So time for an example. You have your house, you found some groundwater under your house and decide to use that. The city water's costing you too much, so you want to make your own little water system here. So you found some groundwater 10 meters below ground, 50 meters away from your house, have some 3 centimeter diameter PVC piping laying around. So you decide to build this little system, and of course to get the water from here into your house, you need a pump. So the question is, what power pump do you need to buy to make this happen, using or to give you a flow rate of 25 liters per minute, because that's determined, that's what you need. So what kind of pump do I need? So to solve this problem, we need the full Bernoulli or energy equation, P1 over gamma, V1 squared over 2G, Z1 pump power or pump gain equals P2 over gamma, V2 squared over 2G, Z2, and my head losses. So my head losses, I'm going to have some major loss through these straight sections. I'm going to have some minor losses, got a bend here, got an entrance, things of that nature. So need 2 points. 2 points you're going to pick are down here, beginning of my pipe system, point 2 over there at the end of my pipe system. So next step is to make this equation simpler. We want to reduce it by eliminating things. So down here, atmospheric pressure. The question didn't state it, but it implied it. I have atmospheric pressure down here. Obviously, I have atmospheric pressure in your house. So P1 equals P2. You can cancel those. V1, my velocity down here, the water's not moving. Need to suck it into the pipe, so that's part of my problem. So V1 is 0. And then last thing, I can pick my Z values to be whatever I want. So I'm going to pick Z1 to be 0, which means that Z2 is 10 meters. So what I'm left with on the left-hand side is just my pump gain, HP. Then on the right-hand side, I have V2 squared over 2G, Z1, and my head loss. Head loss is all my major losses, F, L over D, V2 squared over 2G, and all my minor losses, all my Ks, V2 squared over 2G. So again, these are both V2 because that's what is in the pipe, which means that I can basically take this V2 squared over 2G out. So I'm left with Z1, V2 squared over 2G, 1 plus sum of F, L over D, plus sum of K. Now it's a matter of using values for these. I know Z1, I need to find V2. I know what flow rate, so I need to relate that to flow rate. I need to find my F for my pipes here, and all my minor loss K values. So first one, my velocity V2, again, I can find from the flow rate. V2 is just flow rate divided by area, Q over A. And my area is pi d squared over 4, so V2 is 4Q over pi d squared. I know I want a flow rate of 25 liters per minute, but I want to get that in meters cubed per second basically, so I have the conversion factors from liters to meters cubed. There's 0.001 cubic meters in a liter, and then 60 seconds per minute, so that gets that in the right units. And then pi diameter squared gives me a velocity of 0.59 meters per second in my pipe. The next unknown quantity in my equation is the friction factor, F, for the major losses. So to find the friction factor for major losses, first thing we do is find the Reynolds number, velocity diameter over kinematic viscosity, 0.59 meters per second, 0.03 meters for the diameter, and then kinematic viscosity of water at 15 degrees Celsius, confined in table B5, 1.14 10 to the negative 6 meters squared per second, gives a Reynolds number of 15,500. And then with that, I'm going to need to use it's turbulent. So in the turbulent case, you need to use either the Moody chart or the one of the two equations. For that, we need the value of epsilon. Surface roughness for this pipe, PVC, it's plastic, it's smooth, so epsilon is 0. Then again, by plugging that into the equation or using the Moody chart, you get an F value of 0.028 for this scenario. Then last thing we need are minor loss coefficients for all the minor losses. So looking at my system here, I have a minor loss associated with this entrance. That entrance is reentrant based on the figure. And so the value for that, K, is 0.8. Find that in figure 12.4. Then it comes up, has this 90-degree bend. So I need the K value for a 90-degree bend. Find that to be 0.9 in table 12-2. And then it comes out, and there will be some sort of exit condition, but I don't know what it is. Might be connected to other systems. All I'm worried about for now is getting the water from this groundwater reservoir into my house. Once it's there, I'll worry about that later, basically. So those are all my minor losses for this system. So now I know all the values I need for my equation, so I can plug them all in. So Z1, 10 meters, V2, 0.59 meters per second, square that, divided by 2G, 2 times 9.81 meters per second squared. Then 1, my F value, 0.028, that's in both pipes, it's both the 10 meter part and the 15 meter part. So you can add those together, divide by the diameter, 0.03 meters. Then all my K values, I have a 0.8 and a 0.9 for those. So putting all that together gives me a total pump gain required of 10.46 meters. And then to find the power, multiply that by gamma and Q, the specific weight and the flow rate. So for water, specific weight, 9,810 liters per cubic meter. My head loss, or pump gain, of 10.46 meters. And then Q, 25 liters per minute. Again, convert that to proper units. So end up with 42.8 watts. That's the size pump or power pump that they're going to need to make this work. So last example, a fairly complicated one. You have a gasoline in your car. It needs to go from the gas tank to the carburetor, your engine. Carburetor is 2 feet higher than the gas tank. Goes through a total of 10 feet of fuel line, quarter-inch fuel line made out of drawn tubing. Has 5 bends. You get around things like axles and other various components in your car to get from the gas tank to the carburetor. Then goes through a 1/32 inch jet into the carburetor. Carburetor has a pressure of 14 psi. Fuel tank has a pressure of 14.7 atmospheric pressure. Pump's 80% efficient. Car is using gas at a rate of 0.15 gallons per minute. So how much power does your engine need to supply to your pump to make this all work? So to solve this, helps to have a little diagram to see exactly what's going on. Shove my gas tank down here. I have this 1/4 inch tubing, 5 smooth bends, then it contracts into a 1/32 inch jet, then it goes up into the carburetor. So that's kind of what's going on. Begin with Bernoulli's equation, full energy equation. Then want to make this guy easier. So what can we get rid of? Well, in the gas tank, fuel's not moving, so V1 0. And then I'm going to pick this to be Z1 equals 0, which means my carburetor 2 feet higher. So Z2 is going to be 2 feet. So that's all I can get rid of in this case because my pressures are not the same, but I know what those values are. A few things I don't know: gamma, V2, and all my head losses. So I need to get to that. So now to find a whole bunch of values that I need. So again, gamma, find that in back of the book. For gasoline, table V2, at the gamma value of 42.5 pounds per cubic foot. While I'm there, I'm going to eventually need the kinematic viscosity as well when I find the head loss. So that is 4.9 times 10 to the negative 6 feet squared per second. Diameter, when I do the head loss, is in this 1/4 inch pipe. So I'm going to need that as 2.25 inches. You can divide by 12, get that into feet, 0.021 feet. My flow rate is given in gallons per minute. I don't necessarily want that. I want cubic feet per second. So convert that, 0.15 gallons per minute, 1 minute, 60 seconds. In 1 gallon, there's 0.134 cubic feet. So doing that gives me a flow rate of 3.35 times 10 to the negative 4 cubic feet per second for the flow rate. Then I also want to know V2, what's the velocity coming out of my jet. Remember, my jet is 1/32 of an inch, So flow rate over area, 3.35 times 10 to the negative 4 cubic feet per second divided by pi over 4 diameter, 1/32 of an inch squared. But then I want that in feet, so I have another factor of 1 over 12 squared as well. Gives me 63.3 feet per second as my V2 coming out of that jet. Now, the little problem now is that my head loss is through this pipe. It's not over there. So my head loss, when I calculate it, needs to be through this guy. So I'm going to need not that velocity, because this is velocity coming out of my smaller jet. I'm going to need a different velocity for that guy. So the last thing we need in my equation is the head loss. To find the head loss, it's going to be in this section of pipe. I'm going to call that section 3, because my major losses, that's where they're happening. So major losses, I have F L over D, V3 squared over 2G, and then my minor losses, K, V squared over 2G. Didn't put a number on the V because I'm not sure which one I need yet. So for my major losses though, I need to find this velocity V3. So again, flow rate over area gives me a velocity of 0.99 feet per second in that 1/4 inch drawn tubing. Can then find my Reynolds number, velocity diameter over kinematic viscosity. So 0.99 feet per second, 0.021 feet for the diameter, and 4.9 times 10 to the negative 6 feet squared per second gives me a Reynolds number of 4,240. Above 4,000, so turbulent, meaning we find the friction factor F through either the Moody chart or one of the two equations. To do that, we need the epsilon value. So for drawn tubing, find epsilon to be 0.000005 feet, and then epsilon over D ends up being 2.38 times 10 to the negative 4, and with that value and the value for the Reynolds number, get a friction factor of 0.039, again, either from the Moody chart or one of the two equations. The last thing to do is find our minor losses. So in our system, we have these 5 smooth bends. Figure 12.6 gives us a table for the K values for smooth bends. You can find it to be 0.21 for this value of R over D, radius of curvature of the bend divided by the diameter. So that was given to as 6 in the problem, so K is 0.21. And that happens in this 1/4 inch drawn tubing, so the velocity I need in that case is the velocity through this 1/4 inch drawn tubing, which is what we called V3 before, 0.99 feet per second. Next one, I have this contraction at the very end from a 1/4 inch line to a 1/32 inch line. So contractions are found in figure 12.5. The K values, K value for that is 0.5 based on that chart. Important thing here is that this value is based on the exit condition. So the exit condition is the smaller one, so the velocity I want there is actually V2, the faster one. And then lastly, I have some sort of entrance. I'm going to guess it's re-entrant, even though it doesn't actually say, but that's usually how gas tanks, you need a pipe to go right in there to actually get the gas out, so that makes sense. It's also the worst case scenario. So entrance, K value 0.8, figure 12.4. So those are all my minor losses. Now to put everything together. So rearranging my equation slightly, HP, move the P one to the other side, so P2 minus P1 over gamma. I have V2 squared over 2G, Z2, then all my losses, major loss, FL over D, which is depending on V3. I have some K values that depend on V3. Then I have the K for the contraction, which depends on V2. So putting all those numbers in, 14 minus 14.7, convert that into PSF, multiply by 144, divided by the gamma value, V2, 63.3 squared over 2 times 32.2, Z2 is 2 feet, and then V3, 0.99, F value, 0.039, length of 10 feet, diameter, 0.021 feet, and then all my K values that depend on V3 are my smooth bends. I have 5 of them, so 5 smooth bends, 0.21 for the K values, follow those, entrance of 0.8, and then the contraction, K value 0.5, that depends on V2, 63.3. So all that together gives me 93.3 feet as my necessary pump gain. And then finally, you want to take that pump gain, convert it to a power. So pump gain times specific weight times flow rate gives me power. So 93.3 feet for my pump gain, 42.5 specific weight and flow rate 3.35 times 10 to the negative 4 feet cubed per second gives 1.33 pound-feet per second of power. Now, of course, my pump is only 80% efficient, so to actually get the power that we require to give it, you need to divide that by 0.8. So 1.66 foot-pounds per second is what power we actually need to give to the pump. In terms of horsepower, that's roughly 3 times 10 to the negative third horsepower. So that's what we need to our pump to get fuel to the carburetor.